Hello friends, welcome to my YouTube channel Weathercast. Today's educational video is on a very important topic which is thermocline, which I like to call mystery in the ocean. Alright, so not many people know about thermocline, but this particular feature in the ocean plays a very important role in governing the weather dynamics. So that is what we are going to look into today. And this is I have tried to make this a very basic video with a lot of fundamental explanations. So let us just see how this thermocline plays a very important role in weather dynamics. So what is a thermocline? It's the part of the ocean where the strongest gradients of temperature exist. So if you look at the ocean, it has warmer water on the top and colder water on the bottom. In between region is the region where the thermocline usually exists. And if you look at a typical pattern of the thermocline, it is the strongest gradient. So there is this temperature which is constant, and then there is a sharp gradient. That is the gradient which determines the thermocline, or that is the region where the thermocline sits. So above the thermocline, usually the fluid is well mixed, and the reason is very straightforward. It's because near the top of the ocean is where a lot of energy is there, the wind energy or the solar energy or any other turbulent energy that's kind of mixes the upper layer, and hence you have an upper layer and then followed by the thermocline beneath it. The dynamics of the thermocline are very important because they are the one which govern the surface of the ocean. So basically if you look at the SST, the sea surface temperature, that has a very strong link to the thermocline, because thermocline is generally where the cold water exists, and the relation or the coupling between the sea surface temperature and thermocline decides what should be the temperature of the surface, and that is exactly what is going to kickstart the evaporation, convection, or any process with the atmosphere. So although the sea surface temperature is the face of the ocean, whatever is happening beneath is the energetic part. That's, if you shut that off, then SST will not evolve, right? So everything is tied down to the bottom. The reason we talk about SST a lot is because we are able to see it. We are able to have a feel for it from the satellite images. However, all of that is basically governed by the underwater dynamics or the thermocline dynamics. Okay, and hence it is very important to understand how the thermocline behaves, and we have to do some kind of modeling studies because you cannot see a thermocline from the satellite. Okay, and that's what makes thermocline a very important feature and a very difficult feature to understand. So this is a typical pattern in the ocean where you have the top few layers are well mixed, and then you have the sharp gradient, which is the thermocline. Okay, so this is a typical thermocline in the bottom. Most of the time we ignore this part after 1,000 meters because not much activity is happening, because it is the solar radiation doesn't reach there, the wind energy doesn't reach there. So usually with this, it is this top 500 or 700 meters is where we are interested in modeling the ocean. Alright, so thermocline has a different behavior in mid-latitude and the tropics, because in the tropics there is a lot of solar insolation, or the solar radiation is very strong. So upper layer gets heated up very strongly, leading to a very shallow thermocline. Okay, so the thermocline is very shallow because you have a lot of heat trapped in the upper layer, and that heat, it doesn't go down, and hence you start the cold layers of water, and you start with a very shallow thermocline. Shallow in the sense the thermocline is very close to the surface. Whereas in the mid latitude, because the solar insolation is not much, so the top surface is not getting heated up much. That's why you have a very deep thermocline. Okay, and the thermocline is also not very strong, right? If you look at the gradient, right? So if you look at the slope is very strong, whereas the slope is very weak. Okay. All right. So this is the mid latitude. So mid latitude thermocline has a seasonal pattern where during winter it is not very sharp and deep, whereas during summer it becomes shallow and sharp. Okay, whereas in the tropical region the thermocline is always the same, where it is always sharp and shallow. Okay, so this is important aspect of a thermocline. Now, what does this winter and thermocline, summer thermocline mean? So, thermocline during summer is shallow because of solar heating, which we already saw, and this results in a very thin mixed layer. So, the mixed layer is very thin. Whereas during winter, the surface instability helps in a deeper thermocline, and hence the thermocline is deeper. Okay, so summer thermoclines are very shallow, whereas winter thermoclines are deeper. This is one thing that we have to understand. What are the repercussions? We will talk later. So there is a thermocline in the atmosphere as well. We always talk about thermocline in ocean because that is the most important aspect. But in the atmosphere also there is a thermocline which we call as inversion. Okay, so there is an inversion layer. Usually, what happens in atmosphere is that the hot air is here and then warm air is above. So the mixing is always happening. Whereas you reach a stage where the column stability changes, where you have colder air here and warmer air here on the top, which is known as the inversion layer, and that is the surrogate of a thermocline in atmosphere. But this is just a analogy that I'm drawing, but in the next slides, I'm only going to talk about the ocean thermocline. Alright, so what are the factors that govern the thermocline? One is the solar insolation, which we already talked about. The second is the wind. If the wind is strong, then the thermocline will be strong because it will mix up or stir up the ocean, leading to a very thick or very deep mixed layer. Okay, and a thermocline will be much below from the surface. And lastly, there is something known as upwelling and downwelling, which is a product of Ekman transport. So upwelling leads to a shallow thermocline, while downwelling leads to a deep thermocline. So what is the repercussion of this Ekman transport? So in one slide, Ekman transport is nothing but if the winds blow from north to south, then the entire water is going to be pushed to the west. Okay, and because of that, the loss of water, there has to be water from the bottom which is going to come up because continuity has to happen. If some water has been taken from some place, then some water from some other place has to come in. So this deep water will come up. This deep water is cold. As this deep water comes up, it pushes the thermocline up. All right, that's what is known as the shoaling or heaving of a thermocline. Okay, and that is the upwelling process. Downwelling process is one when the water is being pushed down, and that will be the reason why the thermocline will be pushed deeper below. Alright, so this is the upwelling and downwelling due to Ekman transport. Now, what is the importance of this? The importance of this is an equatorial thermocline, and which helps in the formation of El Nino. Okay, so during a neutral condition, let us take the Pacific because El Nino is in that region. So blue is the thermocline, right? With latitude, how it is how is it changing with longitude? So what happens generally is that there is upwelling in the West Pacific and there is downwelling in the East Pacific. So this makes the thermocline shallow in the Eastern Pacific, whereas it makes the thermocline deeper in the Western Pacific. A shallow thermocline created due to upwelling and downwelling phenomenon means that there is a lot of cold water in this region, which is because the upwelling has pulled all the water from the bottom to top, whereas the downwelling is the surface water is going down. That means hot water is going down. Okay, so when we are talking about the formation of thermocline due to upwelling and downwelling, upwelling means colder water and a shallow thermocline. Downwelling means warmer water and a deep thermocline. Okay, so because of this gradient in thermocline which is created, where there is a deep thermocline here and there is a shallow thermocline here, a lot of air or moisture is being pushed towards the Western Pacific, leading to cloud formation because there is a pool of warm water. And this is the mixed layer because, since I already explained in my first slide, anything above the thermocline is a mixed layer. So this mixed layer has a lot of warm water in it, which helps in evaporation and formation of cloud formation. This is the neutral condition in Pacific. Okay. During El Nino, what happens is that there is upwelling and downwelling patterns are reversed. There is upwelling now in the Western Pacific and there is downwelling near the Eastern Pacific, because of which the thermocline maintains a very steady state throughout. Compare this thermocline has a gradient where this is above, this is below, whereas here during El Nino the thermoclines is almost straight line. Okay, so there is no gradient in the thermocline, which means that the winds are very weak and the water is not this. There is no preferential warm water which is available in the western side. All the warm water is now in the central Pacific, which leads to formation of clouds in the central Pacific, and hence El Nino type condition where there is drought like conditions in Asia. All right, I hope it is clear. All right, La Nina conditions are very different, where the thermocline has a much sharper gradient because upwelling is strong, downwelling is strong, and the thermocline will be even stronger. So this gradient, this slope will be very strong, and that will allow for a much warmer water in the western Pacific, which will give La Nina type conditions and good rainfall for Asian subcontinents. Okay. So this is how the thermocline plays a role in governing the cloud formation and in this kind of interseasonal phenomenon like El Nino or Indian Ocean dipole. Very similar concept holds good for Indian Ocean and the related Indian Ocean dipole. Okay. So this video shows the importance of the heaving of this thermocline, because as the thermocline heaves, it supplies energy to the surface, which is the face of the thermocline, which sets up the sea surface temperature and hence the evaporation. So this is the video from NOAA, which is the nodal US agency. Okay. So what we are seeing here is the Pacific. Okay. I'm sorry. Yeah. So if you look at this Pacific, on the top is the top view, and here is the side view. On this side is the side view. This is the thermocline. So you can see that during El Nino, the thermocline is very shallow. Sorry, the thermocline has no gradient, right? It's almost a straight line, and that's how you figure out that El Nino is developing. Okay, and this was the 1997-98 El Nino, which was very strong. And as neutral or La Nina conditions prevail, then you can see that the thermocline has now has a slope, where this is downwelling and this is upwelling, right? So there is a slope of thermocline, and there is this warm pool of water which is lying here, which will ensure that good convection takes place. And if you look at the same warm water during the El Nino conditions, then you will see that all the warm water is in the central Pacific, which doesn't allow any preferential cloud formation in the western Pacific. Okay, so you can watch this video when you have time fully. It's available online through NOAA's website. Okay. All right. So due to the upwelling and downwelling, the mixed layer is deeper. That means the greater pool of water or warm water is available in that region, and hence there is a good likelihood of convection. And since the ocean temperature is the measure of energy, you have a lot of convection, and the ocean temperature is a measure of energy, but the thermocline is the source, because the thermocline is the one that determines how much energy should be stored in that particular region. Okay. All right. So one note is that if the mixed layer is too deep, then it could mix with the cold water from underneath, because remember there is a thermocline, and then below that there is a very cold water, which is the deep ocean. So if it is too deep, then also convection is not going to be very strong. So thermocline helps in regulating this particular phenomenon, where it ensures that there is an optimum sea surface temperature which will allow for convection. Alright, so I just want to cover one more thing before I wrap up. There are thermocline forming due to upwelling and downwelling, that is very clear. That is mostly in the equatorial ocean, equatorial Indian Ocean and equatorial Pacific Ocean. But thermocline can also form or can be modulated due to strong winds and instability. Okay, so one of the common things that prevails is that, so what I told here is that the deeper thermocline is good because it has a deep mixed layer, okay, and it will help in producing convection. That is only true for upwelling and downwelling kind of phenomenon, because downwelling means warmer water on the surface is going down, and that's why it is deepening the thermocline. Okay. However, for a basin like Bay of Bengal, which has a very shallow thermocline but has a lot of activity, so this is kind of counterintuitive, right? It's shallow thermocline means very shallow mixed layer. Shallow mixed layer means not much energy, correct? That is what we have read, that we have understood so far. But when the thermocline is set up, or when the thermocline is governed by the strong winds and instability, what happens is a shallow thermocline is advantageous, because If there is a strong wind and instability, then the upper surface of the ocean will get thoroughly mixed with the bottom surface, or it will mix with the colder water at the bottom. And because of the presence of hot and cold water mixing, the temperature will be regulated to, let us say, 23, 24, 25 degrees Celsius. Okay, that is what happens in the Arabian Sea, where the thermocline is deep, but the sea surface temperature is not very high. Okay. On the other hand, in the Bay of Bengal, the thermocline is shallow and the sea surface temperature is very high because because the winds are weak, because of which there is not much mixing. So thermocline is also very shallow, it is close to the surface. So most of the heat is trapped within the top few meters. And that heat is the one that provides the convective potential for cyclones to form in Bay of Bengal. This is the reason. So upwelling and downwelling is one mechanism, but that mechanism requires a deeper thermocline, is beneficial because that will make the mixed layer very deep and allow for a lot of convection. But thermoclines that are formed due to strong winds and instability require a shallow thermocline, because the shallow thermocline will ensure that the upper layer and the bottom layer, which is cold, hot and cold respectively, upper layer is hot, bottom layer is cold, they don't mix too much. Thereby the upper layer maintains its hot energy or heat energy, and it still gets more heated up because of the solar insolation, and then it has the potential to produce more convective storms. Right? This is the reason why Bay of Bengal, even though it has a shallow thermocline compared to Arabian Sea, the sea surface temperature is very higher, and the cyclone potential is also very high in Bay of Bengal. This is the general scenario except in monsoon months, because during monsoon months winds are very strong. We know that. Because of the strong winds, thermoclines become deeper and the mixed layer also becomes deeper. Okay. So during monsoon times, we don't have storms, we don't have cyclones, right? And that's why during monsoon, it is mostly the low pressure systems which kind of take over and produce the rainfall that is present. So, alright, so what governs the thermocline? Because since I said that thermocline is something which we don't see physically, so therefore it has to be modeled. So in order to model that, we need to understand the governing parameters for a thermocline. Those are the solar radiation, the wind, the upwelling and downwelling, which are the mesoscale processes. The global ocean circulation, where water flows from poles all the way to equator, that also governs the thermocline, or the shape of the thermocline, whether it is deep or shallow. Waves in the ocean, like Rossby waves, Kelvin waves, that also govern the thermocline. So these are the mesoscale systems that govern the thermocline. And on a submesoscale, and which are hardest to capture, those are the turbulence and eddies in the ocean that govern the movement of the thermocline. Alright, so I want to say this again. SST is just the face of the ocean. The sea surface temperature is just the face of the ocean. Everything below that is what governs the sea surface temperature, and that's the only reason why this thermocline is a very important concept which we have to embrace, and a lot of research activity or a lot of research work has to go into this thermocline behavior, which will help us in predicting the weather patterns and also the monsoon patterns in a very nice and accurate manner. I hope this video was useful and it gave a different flavor of a new mechanism in ocean. And if you like this, please share this video and subscribe to this channel for regular educational videos related to weather. Thank you. Until then, goodbye.